All right, the record is on. So the last time we learned how to use the Muller-Breslau principle to develop the qualitative influence line, right? You get to have the shape, and then once you have the shape, you can try applying the unit load to get the quantitative influence line, the influence line with the numbers. So now it's time to learn how to use what we have from the last time. So the use of influence line, it's pretty straightforward, really, and nothing much to talk about. But let's have a quick visit, okay? Because it is, of course, the line that is made of the placing the unit load anywhere in the load. So when you have the ordinates, and now you have the real load with the concentrated load acting on it, you could just multiply the concentrated load with the ordinate of the influence line, and you get the values of the design function right away, because the influence line is made of the unit load, right? So when you have the concentrated load, you can just multiply the magnitude of the concentrated load with the ordinate at the corresponding location that the concentrated load is applied. Simple as that. But when it comes to the uniform load, now the uniform load will cover the length of the influence line, which may not be a constant. So you cannot just multiply it right away. We need to perform a little thing called integration. Okay, so now we can look at this small strip. Okay, multiply by the magnitude of the load W. This small strip is dx. And then the height of the influence line or the ordinate is y. We simply carry out this, but W is a uniform load, is a constant. So you can bring this out of the integral and you are left with a y dx integral, which is of course the area. So simply put, when you have the uniform load, you just need to multiply the uniform load by the area under the influence line which the load covers. So it's simple enough. So I'm not going to be so cruel as to, try to give you the load that is not constant like this. But if you have something like this, you now know that W becomes a part of your integral, right? So you have to perform that. So I just hope that you know that. Okay. All right. So pretty simple. If you have the concentrated load, you multiply that with the ordinate of the influence line. If you have the uniform load, you multiply the uniform load itself by the area of the influence line, which the load itself covers. Okay, so let's head back to the example. Okay, oops, wrong subject. Okay, here we are. Example number 27. Use the influence line developed in the previous example to calculate values of those design functions. If, let's say if that's a beam, and then there is Mr. M, weighs 85 kilos, standing on the tip of the beam. Okay, let's say what design function are we going to calculate? We can calculate as many as we want, but it seems pointless to me to repeat the thing. So let us try to, okay. So let's say, where am I? Okay, would it be a good idea to try to copy this? Maybe not, okay? So let's try reaction at B. Now this is the influence line that we have, the ordinate 1.5, okay? And the span length is 2 and 4. Okay, so I'm just going to take that down here. So that's the influence line of, say, RA. Okay, this line is ugly. Now let me try to draw a nicer line. Okay, better. It is 1.5 in the end, okay, and this is 6 meters. And our support is right there. So if Mr. M stands here, 85, okay, and then Miss Q weight 45 following Mr. M to the point 0.5 meter left of B. So support B, 0.5 meters. So that would be this about this location, okay? Because to write down 6 meters here would not be a good idea. So this would be 4 meters, right? We have the support here and then 2 meters. So if Miss Q, who weighs 45, will stand 0.5 left, so she's about here. That's 2 meters, so 0.5 is about here. So there's another person with 45 kilograms here, and then there's another Mr. X, who weighs 70, following Miss Q until 1 meter right of, oops, right of what? I missed it. Hang on. One meter from right of B, okay? I don't know where it went. So we have another one at about 1 meter from here. 70. Okay? And RB, right? That's RB, right? Not RA, sorry. It should be B. Okay, so RB here would be pretty straightforward if you could obtain the ordinate here. 85 is on the tip, so the ordinate is 1.5, right? 45 here is at the location 0.5 meters from the support, so you can say this is about 4.5 meters, right? From this end of the triangle. So this ordinate would be equal to 1.5 multiplied by 4.5 over 6, right? Because right here is 0.5 from the support. So that means this distance is 4.5 meters. Okay, so it's 4.5 over 6, which is equal to 1 and 1/8. And then we have another one here. This guy is 3 meters, 1 meter away from the support. So that leaves this as 3 meters. Okay, so that means this ordinate is 1.5 and then 3 over 6, which is equal to 3/4. Okay, so now after with all the ordinates, you can now calculate the RB. Okay, so RB is going to be equal to 85. You know, that's a kilogram. If you really have to be precise about the force, you must multiply that by G, right? So anyway, you know that. So it's 85, which is right there, multiplied by the ordinate 1.5, then 45, multiplied by the ordinate 1 and 1/8, and then 70 multiplied by 0.75. So that's that covers the 3 concentrated loads, right? But we have another one here. Let's do it all together. That it says that if there's also a uniform load of 200 kilonewton per meter acting on the entire beam. So the reaction from this uniform load will have to add the the effect from the uniform load as well. So that's to have to be precise. The first term will have to be multiplied by the G, right? Because that's a kilogram force. That's a kilonewton. Okay, so this has to be multiplied by G, and then 200. Because it's a uniform load covering the entire beam, so we need to multiply this with the area of this triangle. Okay, so it's the half of the height of this triangle is 1.5, as you can see, and the length is 6. Okay, so that should give us the answer. Okay. So I'm not sure about my final number, but it should be correct. Okay, So that would be, I think the point load will give you 230, about 230, and then plus the area. This is 90. Okay, so that's how we do it. Let's do another one. We can also calculate the RD. Okay, and then RD, we would have this. Let's remove RD first. Let me draw the influence line first. Okay. Oops. Doesn't seem to be able to draw the straight line today. The RD we have here is something that looks like this, right? Now you have to be mindful of the sign of the influence line, of course, because you can both have the upward and downward forces, right? So this is the influence line of RD. We have -5 here. We also have 1 here. Okay, so it goes without saying that we need the ordinates. Right here, we already have that. And then because Miss Q is right here at the location 0.5. So this ordinate is -0.5. Now it's only a quarter of this, right? Is 0.5 over 2. That would be the height, which is equal to 1/8. And then Mr. X, probably, yeah. Mr. X is 1 meter at this location, 1 meter at this triangle. So it's a quarter of this. So I don't think I need to do the calculation, right? So it's a quarter. So you can see now RD is going to be equal to 85 multiplied by -0.5 plus 45 multiplied by minus, oops, it's supposed to have minus here too as well. That's not nice. Let me move it a little bit. Okay. Right, this is minus. So, okay. 45 multiplied by -1/8, then plus another, which is 70. Oops, I forgot the G, right? This is supposed to be multiplied by G as well. 30G, sorry. Back here, 70 multiplied by a quarter. Again, because this is kilogram for, so I have to multiply that by G. And if that is also the uniform load, it's 200. But now you see you have the area with the positive value here and then the negative value here. So be mindful of that. Okay, so it's going to be the positive area. It's a half of 1. The base is 4 and then the height is 1 minus a half of the base is 2 and then the ordinate is 0.5. So it's straightforward enough. Okay, and because I have mentioned that we should do RB, RD, MB, and then MC. MB. B is our support, right? So MB, that's right there. Okay, so the influence line of MB looks like this. Okay, with the value here is -2. Remember, the rest is 0. If you want to be complete, okay. So we only, that means if you consider the moment at B, Mr. X will not have any effect on moment at B at all, right? MB is a support, is a moment at the support, and you will only have the moment at the support of this overhanging beam only when there's a load outside in the area of the overhanging beam, correct? So MB here will simply be equal to 85 multiply by -2, and then Miss Q, which is here. So she is at this location, and this is equal to -2 multiplied by 0.5 over 2, right? A quarter of that, which is equal to -0.5, I suppose. Okay, so there we have it, plus 45 multiplied by -0.5. This will be multiplied by G. And then, because we only have the influence line here, so your uniform load will have to be multiplied by this area only, which is 1/2. The base is 2, and then the value is -2. So that's MB. Okay, I think it's pretty straightforward enough. The last one is MC. Where the heck is C? Let me go back and check. Am I going too quickly, folks? Let's see, it's midspan. Okay, so that's MB. Then for MC, you have something like this, I suppose. It's an influence line of MC. We have 1 and then -1. Okay, so I suppose it's straightforward enough, but let's try to complete the job. The ordinate here would be -1 multiplied by 0.5 over 2, where Miss Q is, that's -1/4. And where Mr. X is 1 meter from the support, so that's where it is. So that's 1 multiplied by, because the triangle is only a half of the length of the beam, so it's a half. Okay, so that's 0.5. Okay, so, and we repeat, same thing. All right, which is, don't multiply the ordinates. MC would be equal to 85 multiplied by -1, 40 plus 45 multiplied by -1/4, plus 70 multiplied by 1/4, so a half, sorry. And we multiply this whole thing by G. And then for the uniform load, we both have the negative area and the positive area. So we have to split them. And then the negative area is a half. The base is 2. Height is -1. Plus the positive area, the half, the base is 4. The height is 1. So that's what it is. Okay. Is there any question? Hello? You want me to move up or move down the screen? Are you catching up? Hello?
Can you go up, teacher?
Yeah, sure.
Okay.
Fine enough. Can I, maybe I should, shrink the screen a little bit so that you can see the whole thing? Should I do that?
Yes.
Yeah, would be nice, right? Oops. So that's the smallest as I can. Yeah, okay, that'd be better.
Okay, teacher.
So I'll wait for a minute or two then.
Could you explain where the G comes from?
Because I think I'm a bit untidy, so I give the point, the concentrated load or the point load as the mass, because it's a kilogram, and then I give the uniform load as kilonewton. So I just want to be, nice and tidy. So I multiply by the G so that you would not wonder in the end where, why we have the two different units for the load. It's from my mistake, really. Okay. Generally, if you have the load in the same unit, we don't have to multiply by G. It sounds absurd. Right? So, okay. Are you guys done? Put my phone back. Okay. Okay. Guys done? Right? Can I move on? That's a yes then. So in this case, okay, let's show this a little bit more. Oops. You know what? The screen has frozen. So here we go, right? Happens again. I'll try to bring it back. You know, Tuesday morning, like always. Okay, luckily we have it back. So yeah, in case you missed the last one, MC. Okay, so we can move on, right? So now that's one part of the usage of the influence line. When you have the shape and you have the load, you can just multiply the load with the ordinates and you get the values of the design function right away, rather than calculating everything, okay, by using equilibrium and so and so. So, but that's not it. You know, we have mentioned the fact that we have the moving load. And the most important thing about the moving load is just to find its location or the placement that will give you the worst kind of values, okay? Or you can say the worst case scenario. So we have to study this. It's called the placement for the maximum effect, okay? We need to find the location where, you know, the placement of the load will give you the maximum reaction, the maximum shear, or the maximum mole, okay? Or the critical position. I don't even remember the name, but yeah, you know what I mean. So the first one, you know, instead of trying to place, you know, the load all over the place and come up with the worst case scenario, of course, we engineers must have some kind of approach or method that will help ease the pain. The first one is called the increase-decrease method. Okay. This one is used to detect the change of the shear and the reaction. Okay. So let's say when you have the load right here, and it moves up the influence line from point 1 to point 2. Okay, what is going to change is the coordinates, okay, both x1 and then x to x2 and then y1 to y2. So when we consider this, if you multiply the load with the value of the influence line, you get the design function, right? So I can say whatever the function is, you know, reaction or shear, the design function here will be equal to P multiplied by y1 at location number 1, right? Just the load multiplied by the height of the influence line. And likewise, at point 2, you get P multiplied by y2. All right, simple enough. The magnitude of the load multiplied by the height of your influence line. So the change of the design function, or delta F, F2 minus F1, is going to be equal to the change of the height, right? Which is P multiplied by y2 minus y1. Okay, we still follow this, right? That is simply the change of the value of the design function. But, you know, this is not easy enough. So we can say, we can also draw this because we have the slope, right? And that is dy, that's dx. We can say that dy by dx is equal to, the change of the ordinate in y direction, and then the change of the ordinate in x direction. So instead of trying to, come up with the values of the y all the time, we can, place this, because now y2 minus y1 is going to be equal to dy by dx multiplied by x2 minus x1, right? Now we place this back into this, and therefore this parenthesis is replaced by this. You see, the first one, you have to calculate the height of the influence line at each location, like all the time. But now when the load moves, if you know how much it moves, that is the distance that your load moved, right? x2 minus x1, which is easier than to try to calculate the new ordinates all the time. And then dy by dx is just the slope of your influence line, which if you have the influence line already, to obtain the slope will be just like a gimmick. And then this is just the distance of the load that load moves. Okay, so we now can obtain the change of the design function by simply multiplying the load with the distance that it moves and then with the slope of the influence line. Easier than to calculate the height of each ordinate. But that's the first one. It's the increase-decrease method. And you can make note that this is, say, good for reactions and shear. Okay? Is there any question? Is there any question? I suppose we should wait and see the example, which is a lot easier to see. Okay. Now the second one, lately I haven't seen the usefulness of using this much, so I'm not going to mention this. Okay, just to prove that the placement of the load will create the maximum moment at one particular location, because it doesn't benefit us that much. So now let us move to the third one. Okay, this is much more useful. Okay, that we try to find the load that will give you the maximum positive bending moment on a simple beam. Okay, now this is much more important, because when you design the load, you don't want the maximum load at any particular location. We want the load, the maximum moment that will produce the maximum moment. And this maximum moment, we don't even know where it's going to occur on the beam. So we need to find the location of the load first, and then we will be able to calculate the biggest, the largest, the worst maximum moment. So that gives us some kind of mystery, Okay, so let us look at this. Let's say I have the load group, okay? And when I have the load group, what I can do is I can calculate the resultant of the load group. So Q is the resultant. It's kind of a cute word, but the thing is, it's just the total load, the total load of the entire group. So, okay, let's say if I somehow think that this is going to be my assumption that gives me the maximum bending moment. Okay, now I'm going to place this load group here. Now let's say if we assume that my maximum moment occur here. Remember, this is something that you should always recognize, that your maximum moment, if you have a series of point load like this, would have to occur underneath one of the loads, right? Because your shear force diagram is going to look like this, whatever that is, right? Because we have the point load. So this is where your maximum moment is going to occur, where the shear turns from positive to negative, because right here shear is 0. So it has to occur underneath one of these loads. Okay. All right. So now let's say we assume that the maximum moment is going to occur underneath this P3. So I can write my moment equation. This is a basic free body diagram. Nothing fancy about it. Just cut it. And we have the load P1 and then P2. And then we also have the reaction. But now instead of writing the reaction like this, right now I have the reaction written in terms of Q. Do you realize that whenever you have that, this is another way that you can write the equation. Whatever the load you have, if you can present your total load on the beam as a Q, and you can of course find the location of this resultant force, you can easily calculate the reaction, right? So let's say Q is at the location X. That means this reaction, when you take the moment here, you get that reaction, right? When you take the moment here, your Q is multiplied by L minus X, right? Because if that's X, that is L minus X. So when you take the moment here at this location, it's Q multiplied by L minus X divided by L. So that's your reaction. So I can now write my moment equation like this. This is my R. Okay, and let's say if this is how I'm going to place my load, the X is the distance from the support to the resultant, and then the distance from this resultant to load P3, where I assume the maximum moment is going to occur, it's just another S. So this becomes the reaction multiplied by X plus S. Okay, then minus P1 multiplied by this distance from P1 to P3, and then P2, and then so on and so forth. Okay, so we now know that in order to have the maximum moment, your shear must be 0, just like this picture, you see. And you know that the derivative of moment is equal to shear. So I can just take the derivative of this equation. Okay, and that's it. Take the moment, take the derivative, and you see this term, it has no X, it's just a constant value. And so is this one. So it doesn't matter how many P's you have, this term will be gone, and that too will be gone. And when you take the derivative of this one, you are left with just this. Okay, just take quick derivative. Okay, so because the maximum moment will occur at the location where shear is 0, so we have to set this one equal to 0. Okay, and you see Q is the resultant, L is the span length, can't be 0. The only way that this term can be 0 is that the number in the bracket must be 0. So from this, we now have L minus S minus 2X is equal to 0. So that leaves us this term to prove that when you are going to have the maximum moment occurring on your beam, your load must be placed so that, you see, X is equal to L over 2 minus S over 2. It means that in order to have the maximum moment, listen carefully, the placement of the load will be such that the Q here and the P3 here, they must be, at the equal distance from the center line of the beam. So this is the center line of the beam because it's L over 2, right? In order to have the maximum moment, you must place the load such that this distance, which is the distance from the midspan to the Q, is equal to this distance, which is the distance from the midspan to the load closest to the Q. Okay, so these two distances are equal. So from this knowledge, it means that once you can locate where the resultant is, you see which load is closer to the Q and try to place your load group such that the distance between the resultant to the midspan and the load closest to the resultant to the midspan are equal. Now we have two new knowledge. The first one is the increase-decrease method to use for the maximum shear and reaction, and then this one is for maximum moment. Okay, and you know, it happens every year that generally the examples will be much better than the direct explanation to this. But anyway, before we go to see the example, I just want to ask you if you have any questions. Sorry for the disturbance, because yeah, it's not put it on the record. Okay, is there any question?
Teacher, I have question from the formula M math. Why P1 and P2 is minus, teacher? Because different for direction.
Well, you just look at this, the free body diagram. You calculate the moment here, right? You take the moment here. What's the moment?
Oh,
It's
okay.
just moment equation from the free body diagram. Simple as that, right?
Or take moment at point T, right?
Of course, here we don't want to know the shear there. That's why we take the moment there, right? But we know it's zero, right? Shear is zero. Okay. I suppose you can take the moment here as well, but you know, don't be. I think it's kind of unnatural, but that's not going to say that you know, it's going to be wrong or anything, because if the moment is max, shear here is zero too as well, right? Okay. Is there any more question?
From center of the inner beam and Q all way to equal, right? Length, teacher.
Yes. But
Always.
yeah, it has to be equal. But the thing is that sometimes from time to time, I remember running into the case where, you know, that load, not the load closest to Q, you know, sometimes when I place the center line between the Q, you know, the resultant, and the load farther than the one, you know, closer to Q. Sometimes it gives more moment, but it's highly unlikely. So let's say, yeah, first and foremost, you have to place the load so that the two distances are equal. Yes. So we are, hello? Is that somebody say something? Let's say no. So, okay. Actually, you know, the funny thing is that I thought I had another example, and then I turned it on this morning. Wow, actually, I changed the example. So if we have time, we could see more than one example, but it's gonna be kind of crazy because my example is like tough, probably tougher than your homework. It has to be here. Okay, so that's the example. All right. So we now have the case of the group of moving load here. Okay, moving from right to left, like that, on a 50-meter beam. Oops. Okay, so I want to know the maximum moment that this load group will create on this beam. And I want to know how much, say, like maximum positive bending moment. And I also want to know how much shear force at midspan is going to change when load number 4 replaces load number 3 at midspan. So which one you want to do first? Actually, the maximum moment is easier to understand. Okay, so let's say we're gonna do that first. And since we have only 5 minutes left, let's say I can spare this 5 minutes and calculate the easiest thing. Okay, so let's say this thing to do now would be to calculate the Q. The Q, which is the total force, will be, you know, just the summation of all these loads. So it's 4 multiplied, we have 4 15s. So that's 4 multiplied by 15. So that's 64 tons. Okay. The next job is to try to locate where the Q is. And the easiest thing to do is just to take the moment on one of these loads. So I'm just going to take the moment here. Take moment. I take the moment here. Okay. The first load will be eliminated, right? So I will be left with, say, let's call this the X. Okay. Now I have 15 because I take the moment at the first load. I have the first distance to the load, the second load equal to 4.5, right? Oops, here we go again. Yeah. It's the second time. Okay. Okay. So the second load, okay, when I take the moment at the first load here, I have the distance of the second load to the location equal to 4.5. The third load is also 15, so I can just, you know, arrange my mathematics like this. But then the distance of the second load would be 4.5 plus 7.5, that's 12, right? And then third load, which is also 15, so that would mean 12 here plus 13.5 more, so it becomes 25.5, and then the last one we just add another 7.5, so this becomes 33. Okay, then we divide this by the total load, which is 64. So in the end, we have this equal to 17.578 meter. So that means I can now say that's about 12. So my Q will be at this location. 17 point, sorry for the crazy number. Just maybe it helps us to get the final number more accurate. Okay. So that is where the Q is. Okay. So we are going to come back in the second break and try to calculate the maximum moment. But now we have the knowledge. So we know that we are going to have to place this load so that the center line of the beam will be here. Okay. Is there any question? Hello, is there any question? So let me stop the record.